Good morning. My name is Shiritik. My ID number is 21951A05G2. I am from CSEC section. Today we are going to see linear algebra and calculus. My topic is skew circular matrices. Introduction. Has well-known skew circular and circular matrices play a crucial role for solving various differential equations. Authors authors in presented to skew circular matrices as preconditions for linear multi-step formulae based ordinary differential equations course discussed factor block circular and periodic solutions of undamped matrices differential equations using circular matrix considered periodic boundary conditions such that no additional boundary terms will appear after semi-discretization. Some scholars have given various algorithms for the determinants and inverses of non-singular circular matrices. Unfortunately, the computational complexity of the algorithms is very amazing with the order of matrices increasing. However, some authors give the explicit determinants and inverse of circulant and skew circulant involving some famous numbers. For example, Shen et al. Considered circular matrices with Fibonacci and Lucas numbers and presented their explicit determinants and inverse by constructing the transformation matrices in Gave et al. Give explicit determinants and inverse of skew circulant and skew left circulant matrices with Fibonacci and Lucas numbers. In Jiang et al. Discussed the non-singularity of the skew circulant type matrices and presented explicit determinants and inverse matrices of these special matrices. Furthermore, four kinds of norms and bounds for the spread of these matrices are given separately. In Jiang and Hong, give exact determinants of some special circular matrices involving four kinds of famous numbers. Authors discuss the non-singularity of the circular type matrices of presented the explicit determinant of inverse matrices. There are several papers on the norms of some special matrices. Solak established the lower and upper bounds for the spectral norms of circular matrices, which classically Fibonacci and Lucas numbers entries. IPEC investigated and improved estimation for spectral norms of the matrix of these matrices. Application: given a matrix equation Cx equal to B, where C is circular square matrices of size and we can write the equation as the circular convolution C into X equal to B, where C is the first column of C and the vectors C, X and B are cyclically extended in each direction. Using the circular convolution theorem, we can use the discrete Fourier transform to transform the cyclic convolution into component-wise multiplication. Fn into C into X equal to Fn into C F into Fn in into N equal to Fn into B. So that X equal to Fn of Fn power minus 1 into Fn into B V by Fn into C V by into V equals to Z whole transpose. This algorithm search is much faster than the standard Gaussian elimination, especially is the fast Fourier transform, is used. The properties. The normalized eigenvectors of a circular matrix are the Fourier modes, namely Vj I equal to 1 by root n into 1 comma 1 comma omega j comma omega 2 j comma so on omega n omega power n minus 1 j equal to 0 comma 1 comma so on n minus 1, where omega equal to x into 2 pi I by n is a primitive nth root of unity and I is the imaginary unit. The corresponding eigenvalues are given by lambda j equal to c naught plus cn minus 1 omega j plus cn minus 2 omega power 2j plus so on c1 omega power n minus 1 j comma j equal to 0 comma 1 comma so on n minus 1 determinant. As the consequences of the explicit formula for the eigenvalues above the determinant of a circular matrix can be computed as, let's see. Since taking the transpose does not change the eigenvalues of the matrices and matrix and equivalent formula on is, let's see. Any circulant is a matrix polynomial, namely the associated polynomial in the cyclic permutation matrix P. C equal to C naught I plus C1 P plus C2 P square plus so on C n minus 1 P power n minus 1 equal to F of P, where P is given by P equal to the set of n into n circular matrices forms an n-dimensional vector space with respect to addition and scalar multiplication. This space can be interpreted as the space of functions on the cyclic group of order n, Cn, or equivalently as the group ring of Cn. Circular matrices form a commutative algebra since for any two given circular matrices A and B, the sum A plus B is circulant, product AB is circulant, and AB equal to BA. Let P of X be the characteristic polynomial of an n into n circular matrix C, and let P P dash of X be the derivative of P of X. Then the polynomial 1 by n into P naught into X is the characteristic copolynomial of following n minus 1 into n minus 1 submatrix of C. C n minus 1 equal to. Thank you.